So we are live on YouTube, and I'm recording this on the cloud as well. Okay, we are good. So let's get started. There are some viewers, I believe, on YouTube as well. So I'll just tell them that they can post your questions in the chat window as well. Okay. Yes. Okay, so let's get started. So welcome to the Silicon Valley chapter of IEEE Computer Society. I am the chapter chair, Vishnu Pendyala. Ours is the largest chapter in the Silicon Valley section of IEEE. I believe the section itself is the largest in the globe. So we have over 4,000 subscribers in our mailing list and a strong following of over 12,400 on Twitter alone. We are uniquely positioned by the virtue of our location and available expertise. So today's talk is meta algorithms in machine learning. And I am the speaker. So let's get started. So most of you must be knowing the word meta indicates something beyond, a level up, or a higher layer. Meta algorithms in machine learning work on top of the known classification and regression algorithms like decision trees, logistic regression, support vector machines to improve the performance substantially. So these algorithms often fetch top position in the competition leaderboards and are now commonly used in the industry as well. I mean the meta algorithms. So I'll assume that most of you or all of you are already familiar with machine learning concepts and algorithms. If not, there's an introductory or a refresher kind of talk that's coming up on the 14th of June in 2 weeks. And that's going to be in person. So if you are in the Silicon Valley Bay Area, you can attend it in person. It'll be in Semi in Milpitas. If you are remote, that's fine too. You can participate via Zoom or YouTube. But for this talk, I'm assuming that the viewers or the participants already have some background in machine learning. So we all know that parametric models like logistic regression, for instance, they are impacted by bias, right? So bias in machine learning is very similar to the bias in the real world. It basically stems from simplifying assumptions such as age, gender, and so on and so forth, right? In the real world, the simplifying assumption is that certain age, people of certain age are not capable of doing certain things. Similarly, people of certain gender are better in certain things. So these are all highly simplifying assumptions. And they're very error prone because human beings are not that simple, right? We are quite complicated. We are capable of a lot of involved stuff. We cannot be simplified so easily. So just like these simplifying assumptions in the real world result in bias, the simplifying assumptions made in machine learning algorithms also result in bias. So the parametric models have some underlying assumptions and therefore they're impacted by bias. On the other hand, some other models like decision trees are impacted by variance, high variance, right? Variance in one sense indicates rigidity, right? The model cannot generalize well. Just like people cannot adapt to changing environments. When they're rigid, people cannot adapt to changing environments, right? The same thing with machine learning models. If they don't generalize well, and if they are rigidly bound to the training data, they're impacted by variance. So now, we know that almost all the machine learning models are impacted by either bias or the variance. So then the question arises, how do we make the best of both? So a related question is, how do you reduce the risk arising from fluctuations in a stock's price, right? This is a real world analogy. So how do we do it? So the trick is to diversify, right? Don't put all eggs in the same basket. Don't depend on a single machine learning model. Instead, depend on multiple models. Similarly, when evaluating students, it is not a good practice to evaluate students on a single criteria, like final exam alone, or just two criteria, final and midterm. So that's not an ideal way of evaluating students. We want to evaluate using many criteria, right? We want to diversify. So the keyword is diversify, right? So in machine learning as well, to improve the performance of our models, we diversify and use what is called as the meta learning. I keep telling my students that what I teach in classes is how to learn to learn. So that's what happens in meta learning, right? So typically, you take the example of decision tree. In computer science, the trees are uprooted. So you see an uprooted tree here. It's really a decision tree, which is one of the machine learning algorithms typically used for classification and regression problems. So that's how typical learning happens. You can use a model like decision tree, or you can use a model like support vector machine, logistic regression, naive Bayes. So these are all models, right? So these are called base learners. And in quite a few settings, these base learners are often weak learners. So what do you mean by a weak learner? A weak learner is something that is slightly better than a random guess or a coin toss, for instance. So a coin toss, the probability of hitting a head or a tail is 0.5. And a random guess also is something similar. In weak models, the accuracy is slightly better. So the accuracy could be something like 0.55, slightly more than 0.5, right? So we use all these base learners to train the models, right? So that is the learning part. And each of these models will output a predicted value. So in the typical convention, we call it Y1, Y2, so on and so forth. So these are all the values predicted by these models. So we pass a training set here, train the model, and then with the test set, what we do is we generate the predictions from each model. Now, in typical learning, we would have just used one model and then lived with this Y1 prediction. But we want to improve the performance, right? So we want to not just invest in one model, but multiple models. Multiple models result in multiple predictions, probably different predictions as well. It is not guaranteed that all the models predict the same way, right? It could be either classification or regression, but we cannot expect all the models to predict the same way. So we need to somehow use all these predictions to make a better prediction. So we have a aggregation algorithm, right? So some kind of aggregation to aggregate all these predictions and produce the final prediction, right? So that is the idea behind meta learning. So these models can be generated in parallel, or they can be generated in sequence as well. Some of the meta learning methods use parallelism, and some of them do it sequentially. So because we are using multiple models, we can think of these models as an ensemble, right? You know the meaning of ensemble. Ensemble is multiple instruments typically, right? In a choir or something. Ensemble is multiple instruments. Similarly, here ensemble is used to mean multiple machine learning models. So we learn like in school, and then we learn to learn like in industry. For instance, what happens in school is just learning, but the real learning usually happens when you are implementing what you learn, right? You will discover that your learning hasn't been all that perfect, and you'll try to better your learning, like when you join the industry, right? Or academia also, right? Not just industry, but anywhere you use your knowledge is when you improve your learning. So just like in real world, the machine learning models are also learning to learn. So the learning happens using our regular algorithms, and the meta learning happens using some kind of aggregation of the losses. See, these base learners are not perfect, right? Just like our learning in school is not perfect. We are all students when we are in school, right? Our learning is not perfect. So the learning that happens in the base learners is improvised by using an aggregation scheme, or what is called as meta learning, right? So that is the idea behind meta learning, or meta algorithms in machine learning. So meta learning with traditional machine learning is also called as ensemble learning. Meta learning these days at least is more often it refers to the meta learning in deep learning. In traditional machine learning, it mostly goes by ensemble learning, by the name ensemble learning. But the concepts are pretty similar. Towards the end, we are going to cover meta learning that happens in deep learning as well. And in fact, we are going to see how meta learning is basically the essence of deep learning. So if there are any questions, please post them in the chat window. So meta learning. So we all know learning is never perfect. We always incur a loss, right? Nobody graduates. I mean, 4.0 GPA is used to be uncommon, but these days it's quite common. But still, even if you have a 4.0 GPA, you cannot be confident that your learning is perfect, right? Learning is never perfect. Same thing in machine learning. We always incur a loss with machine learning models. So the whole idea behind meta learning is that learning can never be perfected. There is always room for improvement. And in case of meta learning, the room for improvement is in layers, right? So this is still an active area of research, particularly in the deep learning side of things. So meta learning essentially minimizes the losses from the previous round of learning, right? And it is a very big deal for deep learning. You can do quite a lot of things using meta learning when it comes to deep learning. One of the examples is called few-shot learning. So we all know deep learning requires tons of data, right? But few-shot learning is learning from very few data items. So like you show 5 pictures of lion, and the model should be able to recognize a lion. So things like that. So that's called few-shot learning. There's one-shot learning, few-shot learning, k-shot learning, and things like that. So all that is made possible by meta learning. We'll cover that topic towards the end of the talk. And another interesting finding is deep learning itself is a kind of meta learning. The basis for deep learning is essentially meta learning. We'll see how and why also of this towards the end of the talk. So what's the rationale behind meta learning? Why do we even think of meta learning? I mean, intuition is fine. I mean, we covered the intuition so far, but what is the mathematical basis for meta learning. So let us consider 256. I just chose this number for no reason. I just chose it randomly. So let us consider 256 weak learners. So that means they are just better than tossing a coin. Their accuracy is slightly better than 0.5. So they are weak learners. And let us consider the problem of binary classification, which is commonly used. So in binary classification, you have two classes typically represented by -1 and +1. If it is true and false, false could be represented -1 and true could be +1, so on and so forth, right? So let us consider these 256 base learners or weak learners. And we are assuming that the weak learners are uncorrelated. That means they don't have any relation between two learners. So they are totally uncorrelated. And let us assume that the error rate is 0.45. That means the accuracy is 0.55, slightly better than a coin toss, right? So 0.45 is just not acceptable, right? For a model with an accuracy of 0.55 or 55%, it's no good at all, right? So assume that each of these weak learners, the accuracy is 0.55 or the error rate is 0.45. Now, for the ensemble of the 256 weak learners, to make a misclassification, majority of the base learners must misclassify, right? Because we are going to take a vote, typically. That's the aggregation scheme typically used. So in this case, more than 50% of 256 is 129, right? 128 is 50%, so half of it. So we want majority. So 129 of the base learners should actually misclassify. Only then will the ensemble misclassify, assuming that we are using a mode or a majority voting scheme. So this is just like the coin toss experiment. So we use binomial distribution for the probability of the ensemble making a misclassification. So that means the probability of the ensemble making a misclassification is a probability that 129 of them make a misclassification, 130 of them making a misclassification, so on and so forth, and all of them making a misclassification, right? And each of those probability can be computed using the binomial distribution, right? Because this is just like coin toss. So we are going to use binomial distribution to compute the probabilities. So if you, I am assuming you all know the formula for binomial distribution, but just in case you did not, the formula is nothing new. Distribution. So this is the formula for binomial distribution, probability for a binomial distribution, right? So that is exactly what I'm using here. And if you substitute the values, and then there's a binomial calculator also online, you can use that. And you will find that when P is equal to 0.45, that's the error rate, and Q will be 0.55. Q is the chance that it classifies correctly, the ensemble classifies correctly, or rather the weak learner classifies correctly. So that is 0.55. So if you substitute those values, the cumulative probability, the sum of all these probabilities will be 0.04. So we have essentially reduced the error rate from 0.45 to 0.04. This is a very strong learner. When the error rate, when the accuracy is 96%, it certainly can be rather, 96%. It's a good learner, right? Compared to a weak learner, which has an accuracy of 55%. So that is the power of ensembles. So ensembles basically reduce the error rate from a big one like 0.45 to a really small value. So that is the reason why ensembles are often used in competitions. So you take any competition, most of the competition, you take, what is that, Netflix, right? It was a 10 million or 1 million competition, Netflix movie ratings. They use an ensemble as well. Most of the competitions, Kaggle competitions, use ensembles. The reason is this, that's the rationale. So like we talked earlier, so learning happens through single models, like a decision tree. And in case of bagging, there's a meta algorithm called bagging, and also a meta algorithm called Adaboost. In these two cases, the learners, the weak learners, are all decision trees. They're all trees. We use homogeneous base learners in bagging and Adaboost. So we do the same thing. We get the predictions from each of these decision trees and then combine them using some kind of a aggregation scheme. Now comes the big question. To diversify, we do not want to generate the same tree, right? Otherwise, there's no point. If you if it generates the same tree, you're investing all your eggs in the same basket, in the same stock, right? It's as good as that. So that's not good. So we want to generate different trees. So any ideas on how we can generate different trees? The data set is the same. We have only one data set, but we want to generate different looking trees. So any ideas? You can post your answers on chat window. Right, one answer on the chat window is bootstrapping the data set. That's a very good answer. Any other ideas? Yeah, most of the ideas are along the same lines. We have the power of statistics, right? We have the power of sampling. Sampling is essentially reflects the properties of the population. We know that, right? Statistics. So we take the help of statistics. And one of the statistical techniques is bootstrapping, but there are other techniques also, right? So the question is, how can we generate different decision trees from the same training data set? So the training data set has a bunch of x's, x1, x2, so on until xn. And then there is a target variable y, which is the last column, typically of the table, right? So these are our training data set. Now, how can we generate different decision trees from the same training data set? So there are two ways, right? Two broad ways. One is you can perturb x. You can make some changes to these x. That means the x values, or in the training data set. Or you can perturb y, right? You can somehow change the values of the target variable. So those are the two broad common sense ways of generating different data sets, right? To generate the trees. Now, we can perturb x in two ways. One is row-wise, the other is column-wise. But when we do the perturbations, we don't want to introduce any bias. So we do these perturbations randomly so that we are not introducing any bias, right? So everything happens randomly. So perturbing columns is basically the columns will be different in the data set. Perturbing row-wise implies the rows will be different in the data set. So that's what we are going to do. Now, we can perturb X using certain techniques like the answer on the chat window, bootstrap sampling, right? So statistics provides us this bootstrap sampling. So this is obviously row-wise, right? We choose only certain rows for bootstrap sampling. I'll show in the next slide what exactly it means, just in case you are a bit rusty on that topic. But bootstrap sampling is one way. The other is k-fold cross-validation. You divide the data set into k folds, right? So the rows can be divided into k folds, k parts rather, right? So that is the other way. And we will use, we can use each of those parts or each of those folds for our base learner, for training our base learner. So that is other way of perturbing X. And the other way of perturbing X is through what is called as a weighted sampling. What do you mean by perturbing? There's a question on the chat window. Yeah, thanks for that question. Perturbing is basically generating something different, right? Creating a disturbance, right? Because if we use the same data set, same algorithm to generate the decision tree, all the trees will look alike. So we want to, if the trees have to look different, then the data set has to be different. So therefore, the data set has to be perturbed. That means disturbed some way, changed some way. And we are discussing the different ways of changing the values of X's and the Y's, right? And we have to use only noted ways to do this perturbation. We cannot randomly do stuff, right? We have to use statistically proven techniques. So bootstrap sampling is one such technique, right? Similarly, k-fold division of the data set also is another such technique, right? And then weighted sampling is also another technique. So these are different ways to create disturbances in the data set, to create new data sets. We perturb. Perturbations is a word that is commonly used in machine learning, particularly in the research papers. So that's the reason why I use the word perturbation. But essentially what it means is you basically generate a new data set. You disturb the data set in some way, right? So that's the English meaning of perturb, I believe. If you want, you can search perturb. Perturb is basically make anxious or unsettled, make it unsettled, subject to an influence tending to alter the normal or regular state of path. So that's what perturb means. So that is what we are basically doing when we perturb the data set to create new data sets. So weighted sampling is basically we assign weights to the data items, to the rows. And based on the weights, we sample. So rows with higher weights have a better chance of getting included in the sample. So that's the other way you can perturb the rows. And another way to perturb X is what is called as random subspaces. So random subspaces perturbs the data set column wise. So what we do in random subspaces is, just like in case of bootstrap sampling and k-fold sampling or weighted sampling, we choose a few rows, right? We choose a number of rows from the total number of data, total number of rows in the data set. Similarly, in random subspaces, instead of rows, we choose columns. So we randomly choose a set of columns. So this is column-wise perturbations. Random subspaces introduces a column-wise perturbation into the data set to generate newer data set, right? So those are some of the ways you can perturb X. We'll talk about how to perturb Y in a different slide, but this is essentially the idea behind perturbing X. So in case you are not very sure what these mean, I have a slide for each of them, I hope. So for instance, bootstrap sampling. What do you mean by bootstrap sampling? Bootstrap essentially means lifting yourself up, right? That's the English meaning of bootstrap. So there's a question on the chat window, is the same as random forest? So this is a leading question, which I will answer later. So sometimes I may not answer the questions on the chat window for specifically this reason, because leading questions can confuse the listener, but I'll certainly answer the question. So So bootstrap sampling essentially means you're trying to create the population when the entire population is not accessible, right? So it's you're creating something from what do you call, from the ashes or from the ground up, right? That's what is the meaning of bootstrap. So how do you do that? Obviously, we don't have access to the entire population. So we randomly, for instance, the population of the world is 7 billion or something like that, right? We obviously cannot survey the entire sample, the entire population of 7 billion people. So what we do is we sample randomly, of course, but with replacement. So, I mean, 7 billion is too big a number. Let us take a smaller example. A class of size 32 people, students, right? So we know that all 32 students are not going to take the survey. So what we do is we randomly sample the class, and the sampling is with replacement. That means you send the survey to one student, and again, there's a possibility that the same student gets selected for the survey, right? A better example to understand in terms of statistics is you take a bag of balls or marbles, right? So you pick a marble and note its color, and then replace it back into the bag. So the bag always has n number of samples as we started with, right? We are not going to reduce the number of balls or marbles in the bag. All we are going to do is we are going to pick a ball or a marble from the bag and replace it back. So we do that again and again, without looking at the balls or the marbles, of course. So that is the idea behind bootstrap sampling. So we have the same number of samples picked up from the population, which is typically the size of the population, but there will be repetitions, right? So that is the idea behind bootstrap sampling. So every item in the population has a chance of getting picked up, but it's just a chance. It's not necessary that it gets picked up, definitely. So there's a probability of it getting picked up. And the number of times you pick up from the bag is the number of samples inside the bag or items inside the bag, right? So that is the idea of bootstrap sampling. So as you can see, the green ball, you can think of it as a data item or a ball or a marble or whatever. So it got repeated here in the second sample. In the third sample, these are all unique, so we are good. In the fourth sample, also we are good, right? So that is the idea behind bootstrap sampling. So some of the data items can be duplicated. So that is bootstrap sampling. So we'll talk about it in a little more detail later, but this is essentially the idea behind bootstrap sampling. And k-fold sampling is essentially used for cross-validation. We'll not go into cross-validation, but the idea behind k-fold sampling is basically divide the data set into k number of folds. So in this case, the value of k is 5. So we divide the data set into 5 folds, and this helps in cross-validation, right? Okay, now that I've used the term, let me also explain it. So validation is a process of evaluating the model with an objective to improve it, right? So that is the idea behind validation. So for that, what we do is, of course, like always in machine learning, we divide the data set into training and test data. So test data is meant for test. That is the ultimate evaluation. That's the final evaluation. But before even touching the test data, we only work with the training data, even for validation, right? So what we do is we divide the training data into k number of folds, and we do a series of k number of runs. And each of the k parts in turn is used as a test set for the other k-1 parts, or for the model, and the other k-1 parts are used as a training set. So that means you take this first case, right? Folds 2 to 5 are used for training the model, and fold 1 is used to evaluate the model, right? Similarly, so on and so forth. You do the same thing for all the folds. And then you take an average of the accuracies across all these k number of runs. So that gives you the overall level of predictive accuracy of the model. So that is the idea behind cross-validation and k-fold cross-validation. But the important thing to note here is not cross-validation, but dividing the data set into k-folds and using them for different purposes, right? So the k-folds, you should remember that the k-folds are coming from the same distribution of the data, right? So that means they're identically distributed. So the k-folds are identically distributed. So we are not, I mean, they are like samples. So they are very representative of the population, but they are small samples of the population, not the entire sample, right? So that is the key idea behind k-fold sampling. So this comes in handy when we want to perturb the data set. Now comes the next question: how can we perturb y? Any ideas? How can we change the values of y in a proven way? I mean, not unscientific way, but in a proven scientific way. Any ideas? So y is essentially the target variable, right? So what aspect of y typically changes with each iteration on a model in an ensemble? What aspect of y changes? Y changes, right, with each of the runs of the models. So there's an answer on the chat window, but that's not the right answer. So the answer at least I was expecting is the predicted value, right? With every run of the model, with every model, the predicted value from the model changes. So model 1 might, if it's a classification problem, model 1 might say -1, model 2 might say +1, model 3 might again say +1, so on and so forth, right? So the predicted value is changing, particularly in case of regression, right? If it is regression, the first model might say 3, the second model might say 4, the third model might say 3 again, so on and so forth. So the predicted value is changing. And suppose we need to reach a target y taking several steps, iteration, right? In fact, that is what we are anyway going to do because we iterate through the models. So we can know where we stand as an absolute value y hat, which is a predicted value, or as a measure of how far we are from the target, right? So this is the example, right? So y is what we have to predict. This is the correct value, y. This is what is in the training data set. The last column is y, right? But our prediction is y hat. So we can either, how do we know where we stand, where our models stand? We can either look at y hat and say that the model is predicting 3 when the actual value should have been 5. We can say that we are at the stage of 3, predicting 3, or we can say that we are 2 units away from the final prediction. So y minus y hat. So there are 2 ways, right? So what if we use how far we are from the target instead of y? Instead of using the target itself, why not use y minus y bar for our target? So that way you get different values for y for each run of the model, right? And therefore, when the last column changes, the tree also will change, right? So each iteration, we get new values for the target variable, and y is perturbed. That means we get a different model each time. We don't get uh, identical models. So instead of trying to predict y, we predict how far we are from y. That is, we fit the residuals instead of target value. So y is a target value, and y minus y hat is a residual, right? It is whatever is left by predicting y bar, right? So the word used in machine learning parlance is residual. So y minus y hat is basically the residual. And instead of predicting y, we want to predict y minus y hat. So that way we perturb, we get new values of y each time. And we fit models to this new value, these new values, right? We'll see exactly why and how this happens in more detail, but this is the basic idea of perturbing y. Now that brings us to the next question. How can we aggregate the models? So we have all these models which are trained in different ways and differently, so that they produce different uncorrelated predictions, not different, but uncorrelated predictions. So how are we going to combine these models? There are a few ways. One, we already talked, is a majority vote. If majority says, if it's a classification problem, if the majority says +1, then output y as +1. If majority say -1, output -1. So that's for classification. So we are going by the mode. The other way for regression is taking the average of all these predictions. So we are using mean. The other way is to weight. I mean, not all the models are equally important, right? Some models perform better, some models may not perform better. So we don't want to give the same importance to all the models. So we want to give relative importances to models. That means each model will have a weight. So that's the third way of aggregating. We use weighted response. And one of the ways to calculate weights is using machine learning itself. So what are you doing in parametric models like logistic regression? We are calculating the weights, right, for the features, right? So why not use these as the features and then come up with a model, a machine learning model, to compute the relative weights for each of these predictions or each of these models. Each model is a feature, and come up with relative importances for these features. So that is the idea of using a meta model. This is the most important concept, using a meta model in terms of extensibility. I mean, we see the segue from traditional machine learning to deep learning, meta learning and deep learning. For that transition, this meta model idea is very important. But the other ideas are very important also for winning competitions. So for winning competitions, these are typically what has been done, right? So this is a summary. This is the most important takeaway from this talk, I believe. This is a summary that I came up with. So how different ensemble methods perturb the data sets and aggregate the responses for model ensembling. So the ensembling methods which are popular are bagging, random forest. We'll cover each of these. I don't think we will be able to cover all this in 1 hour, but so hopefully you'll bear with me for longer than that. So we're going to cover all these at least briefly. So bagging, random forest, Adaboost, gradient boosting, and stacking are some of the very popular ensemble methods. So bagging uses bootstrap sampling to perturb only the rows, the columns are intact. You use all the columns as they are. You use the Y target variable as it is. And the models are generated in parallel. The decision trees can be generated in parallel. And the aggregation strategy could be mean in case of regression or mode in case of classification. So that is the idea behind bagging. Sorry. So there was a question about random forests. Yes, random forest uses bootstrap sampling for perturbing the rows. That means to generate different rows, we use random bootstrap sampling in random forests. But we also, in addition to bagging, we also perturb the columns, right? Columns are perturbed by using what we talked about in earlier slide, which is random subspaces. So this perturbation can happen for the entire tree, and before beginning to generate the tree, you do the random subspacing. Or for each node, also you can do random subspacing. So for each node, you choose a subset of the features randomly. So that can also be done, or you can do that at the tree level also. So there are two ways for random forest. We will use the Y values as they are, and just like in bagging, we can generate the trees in parallel, and mean or mode, the same thing. Now boosting, coming to boosting, the two popular algorithms are Adaboost and gradient boosting. Adaboost was invented first. So it uses bootstrap sampling, that means sampling with replacement. I don't know if you can call it bootstrap, but by bootstrap, I mean with replacement. So you pick a sample, you pick a data item and replace it back so that it has a chance to be picked up again, right? So that is bootstrap sampling. So we use sampling with replacement with weighting. That means not all rows have the same probability of picking up. So some rows will have higher probability, some rows will have lower probability. So that is the idea behind perturbing the X row-wise for Adaboost. We don't do any column-wise perturbations or the target variable perturbations, but boosting proceeds sequentially. And the aggregation method is weighted response. That means we are not going to give the same importance to all the the weights could be equal as well, but typically we assume certain importance to each of the base learners. So that's the weighted response. And in gradient boosting, we do not perturb X at all. Instead, we perturb the Y value, the target variable value. And how do we do that? We use pseudo residuals. Why is it called pseudo? We know why it is called residuals, right, from the previous slide. But why is it called pseudo residual? I'll come to that in a while. But so we perturb the target variable by using pseudo residuals instead of the original target values. And the response also is aggregated in a weighted fashion, but the weights are all equal in this case in gradient boosting. So the next way of combining or ensembling is stacking. So in stacking, you either do not perturb X or Y or the data set at all, or you use k-fold sampling, right? So stacking can happen in the models can be generated in parallel, and the aggregation strategy is meta model. That is why this stacking principle is very important. So the aggregation is not using some arithmetic means, but instead it uses a machine learning model to compute the relative weights of the base learners. So this essentially summarizes today's talk, right? So I'll ask you a leading question just to set you into a thinking mode. So we perturbed X for all other models, but we don't do it for stacking. What is the reason? I mean, the idea is to generate different models, right? So why don't we perturb the data set for stacking? Something to think about, right? I'll give the answer later. But let us look at the next question. So where do we start? So that like in the very first slide, we talked that the models are impacted by high bias or high variance. So how do we want to start? Do we want to start with high bias or we want to start with high variance? That's the next question. So let us look at both the ways. Let us start with decision trees first. So what happens in decision trees? Decision tree divides the instance space into regions. So it is characterized by high variance because it overfits the data. And then the decision boundary is quite complex. So for instance, you take this small decision tree, attend class in person. So you have COVID, if there are COVID symptoms, is the class video provided? If the class video is not provided, then you attend in person, things like that, right? It's a simple data set. I don't have to explain too much, right? So the decision tree results in horizontal or vertical splits, right? There are, see, if you see the first split, right? Class video, rather, so the first split is on COVID symptoms, right? So COVID symptoms, yes or no? So this vertical line is what splits the entire region into two parts, region 1 and this whole, the remaining region, right? So region 1 is the yes part. So there are COVID symptoms. Then the answer is no, resulting in R1, region R1. Otherwise, split on class video. So the split is R2 versus R3. So as you can see, the more number of these kind of decision splits that we generate, the complex the decision boundary will be, right? There will be a lot of vertical lines and horizontal lines, and we can come up with really complex decision boundaries. So decision tree, high variance, and the decision boundary is also complex. So we can start with high variance as in decision trees, right? So in two-dimensional case like this, the regions are planes, or rather, what do you call, squares or rectangles and things like that, right? So in n dimensions, they will be hypercubes. So decision tree regions will be hypercubes, right? And the hypercubes are formed based on decision splits. So just like the regions were formed based on decision splits like this, each hypercube corresponds to a decision split. So these are all regions which are generated. So the decision boundary can quickly become complex as we add decision splits or decision stumps. So each split like this is called a stump. It has just one node with two leaves. So that is called a decision stump, right? So the more decision stumps we add, the more complex our decision boundary becomes. So just to illustrate, this is a single dimensional case. So in single dimensional case, you can think of the decision tree algorithm as a binning algorithm, right? So you basically go with the averages. You bin the data points and then compute the averages. So this is one bin, this is the second bin, third bin, fourth bin, and so on. So this is just single feature, right? And you can see how complex the decision boundary can be with each of the decision splits, right? So decision trees have high complexity of the decision boundary, and they're impacted by variance. So that is one way we can start. We can start with a highly complex decision boundary decision tree. Or we can start with high bias, like in a decision stump. So decision stump suffers from a high bias. Why? Because your decision stump has only one node, and your decision is completely based on just a single node, right? In this case, you're deciding just based on income, whether the customer is preferred or not preferred. So the decision boundary is very simple. It's just a vertical line. And the bias is very high. Why? Because you're assuming that you can determine a customer's preferred status based on his income, his or her income, which is a very simplifying assumption. So there's a whole lot of bias that you're introducing into the model because of this assumption. So, and obviously the fit also is very poor, right? It's a very weak learner. You can see that this is not the way to model the customers who are aligned in a nonlinear fashion, right? So those are two ways. So either we could start with a completely grown or fully grown decision tree, which has a complex decision boundary, or we can start with a decision stump with a high bias and a very simple decision boundary, which is basically a vertical or a horizontal line. So the two approaches to ensembles, boosting is sequential and bagging is parallel. For boosting, we start with high bias underfitting. So the test error is still very high, right? Imagine this previous slide. The test error for this is really high. I mean, you cannot assume a customer is preferred or not preferred just based on income. So the error is very high. So for boosting, the error is high because of high bias. And for bagging, we generate fully grown decision trees with high variance, overfitted trees. And the test error is still high because of the overfitting and variance. And with the number of iterations, we iterate to generate different models. And as we iterate, we reduce the variance and the complexity of the decision boundary as well. So in case of boosting, we reduce the bias and the complexity, and we increase the complexity of the decision boundary, right? So we start with a simple decision boundary, high bias in boosting, and reduce the bias, increase the complexity of the decision boundary slightly to an optimal value for both, right? That is boosting. In bagging, we start with high variance and slowly reduce the variance, reduce the test error due to variance, and also reduce the complexity of the decision boundary to an optimal value. So these are two different ideas, both of which are very powerful. So it looks like quite a few of you have, you already know random forests based on the chat. You're asking questions about random forests. So let us start with boosting, right? So we'll start with high bias first. So we aggregate the model responses using weights. So we focus on the failures and de-emphasize successes. And a real world example is the socialistic governments, right? Communism, right? What do? They focus on the citizens having difficulties, right? They de-emphasize the successes of the capitalists, the venture, or rather the entrepreneurs and the leaders, and they focus on the citizens having difficulties to bring them up to the mark. So same thing here. In boosting, we focus on the failures and de-emphasize successes. So you can think of boosting as baby steps towards loss minimization. Loss is, you all know machine learning, loss is an important concept. So the goal of machine learning algorithms is to reduce loss. And in meta methods or meta algorithms, we reduce the loss from the previous round of base learning, right? So, and that is done in baby steps. How does a baby learn to walk? So you keep an incentive like a toy or something at a distance and ask the baby to get it, right? So taking faltering baby steps, the infant finally reaches the toy. So the baby tries to improve with each step, learning from the previous mistakes, right? So that is exactly what happens in boosting. And as you can see, each of these baby steps is a decision stump or a short tree, not a fully grown tree, because remember, we start with high bias, not with high variance. So we cannot start with high variance. So we do not grow the tree fully. We grow short trees and preferably stumps, just one node in the tree, like this one. So these are the baby steps. Let us look at more detail, right? So let us talk about the error, loss function, and what would be the initial prediction, right? So because we are taking baby steps, there are errors at each step. So how do we model the error or for the entire dataset loss? If it is just one step, it's error, or for the entire dataset, it's called loss in machine learning, right? So the baby steps really result in a huge error because remember, they are weak learners, right? So they're just better than a coin toss. If you use just one node or one feature to make a decision, you're obviously going to encounter a huge error. So how do you model that error? So the simplest error, like we talked before, is a residual. How far are we from the target? Let us consider the example of regression first. Boosting can be used for both regression and classification, but let us consider the example of regression. So the simplest error is a residual, y minus y hat, and that is what is called as a residual. We all know that, right? How far are we from the target? So this is, if you notice this is same as the negative gradient of the popular loss function for use for regression, the squared error. So for regression, you typically use the squared error, right? For as a loss. So it is given by y minus y hat. Y hat is a prediction. So y minus y hat is to the power 2. I don't want to go into the details why it is used, why it's squared and all that. There are solid reasons for that. So we typically use this loss function for regression. And the negative gradient is same as derivative, right? If it is multiple variables, the derivative we take across all the variables is the gradient. So for simplicity, let us assume gradient and let us use gradient and derivatives or partial derivatives interchangeably, right? So the residual is basically the partial derivative of this loss function with respect to y hat, the prediction, right? If you take the derivative of this with respect to y hat, what do you get? You get 2 times, because the square, you have to apply chain rule. You have to differentiate this with with respect to y minus y hat, and then take the differential or derivative of this with respect to y hat. I hope you remember how to compute the derivative, right? So when you do that, you get 2 times this residual. So basically, the residual is minus half times the derivative or the gradient, right? So you're all with me, I hope. If there is any doubt, please stop me. So to be agnostic to the loss function, right? That means to make the model that we are learning general enough, or the algorithm that we are learning general enough, we don't restrict ourselves to the squared error, but to any loss function. So to be agnostic to the loss function, dou L by dou y hat may not be always in the form of a residual, is called pseudo residual. Why? Because it's not always in the form of a residual. You take hinge laws, you know various kinds of losses, right? Exponential laws, hinge laws, 101 laws, all these losses. And the loss functions are one of the hot research topics, right? You take any research paper, they typically come up with their own loss function, right? So you take any kind of loss function, the derivative can be thought of as a residual, right? But because it's not in the form of y minus y hat, we call it pseudo residual. It's not really residual, but something like a residual. It tells you how far you are from the target value. Now, for the loss to be minimum, you have to equate this residual or the derivative to 0. So for the squared error case, let us take the squared error case again. The residual should sum up to 0. The gradient is basically, the derivative of the gradient is basically the residual. And it's a sum, you have to sum it up across all the data items. So when you sum it up, it should be equal to 0. So if you want a good estimate for y hat, what does it tell you? When you sum this up, what will you get? You will get, see, this is summed up to n number of data items, right? So you get n into the prediction y hat minus all these target variables summed up, the yi is summed up, right? So what is a good estimate for y hat now from this equation? Any answers? So you all understood, right? You take the derivative, you get the residual. You sum up all the residuals and equate it to 0 to find the best value for y hat. Because our goal is to predict y hat, right? Y hat is a prediction. And our model will predict y hat by assigning the gradient to 0. So when you do this summation on the left-hand side and equate it to 0, you get n times y hat is equal to the sum of all the target variables. Yeah, that's right. It's the average of the target variable, all the values for the target variable. So the first baby step is a single leaf with the mean of target values. It's not even a stump, just a leaf. That is a prediction. So that means for every data item, we are going to predict the average of the target variable y. Right? You get that? So the data set is like this, right? So the data set is like this. So we are going to sum up all these values and take the average. That is the initial prediction. And why is that the initial prediction is explained in this slide. We equate the gradient or the derivative to 0. This is from the maximum minima calculus, right? We equate it to 0. And because of that equation, you end up in an average. So the initial guess is a mean of the target. So now we need to take more baby steps summing up to the target. We need to reach our target, right? So we know that residuals tell how bad the base learner is, right? And how far the base learner is from the target variable. We all know that, right? That is the idea behind residual. So how can we bridge the gap, which is a residual left by the base learner? How can we bridge the gap? So how do we, so there's a gap, which is the residual, and now how are we going to fill it up? The idea is, why not generate a series of models, machine learning models, represented by edge B, small b. And what is the argument that this, or the input that this model takes? It's a data set. It's the input variable, features in the data set. So X is the features, right? So generate a series of models, HB, which is a function of the input data set, or basically input a sample of the data set, because we are going to perturb it, right? In some cases. In this case, of course, we don't perturb. In case of boosting, we don't perturb. So why not generate a series of models that try to bridge the gap by predicting not the final target, but the subsequent residuals. So for the first prediction is the average. So obviously it will be way wrong, right? I mean, you take average, why do you need machine learning models, so many models, right? So you try to bridge the gap. So in the next step, the decision tree will predict slightly better than the average, but still there will be some residual. So try to keep on filling that gap by predicting the residuals. And then when you sum up all these residuals, you will eventually get the target variable. That is the idea. So the training data set for each of these models, the base learners, HB, at each step, is not the original training set, XI, YI, but the XI remains the same. We are not going to perturb X. We are not going to change or sample X. Instead, the Y is perturbed. How is it perturbed? By replacing the target variable with the residuals. So instead of YI, we are going to have the prediction for each row I. So YI minus Y hat I is what we get in the last column of the data set, right? So eventually, after doing a number of rounds of these baby steps, generating a number of decision stumps or short trees, you get the final prediction by summing up the predictions of the models, right? The base learners, the decision stumps, right? Because these are all residuals. How far we are from the target is computed by this. When we sum them up, we should get the original target, right? Now, that is the idea behind gradient boosting, right? Now you will see a new symbol B introduced. So B obviously stands for the number of base learners, total number of base learners, right? And you also see a new symbol lambda. What is lambda? Can somebody from your machine learning knowledge tell me what could this lambda be doing? I mean, I gave the answer here. It is basically the regularization parameter to slow the learning process and avoid overfitting. So if you don't use this shrinkage parameter or the regularization parameter, lambda, so regularization in statistics is called shrinkage, right? So if you don't use it, we will fill in the gap pretty quickly in very few steps. And in doing so, we are going to overfit. We have not spent enough time learning to generalize. So when you memorize your textbook, for instance, important questions, and then get a good grade in the exam, are you learning better? No, right? You're overfitting to the question bank, not to generalized textbooks, right? The same thing will happen if you don't introduce the shrinkage parameter. When you take quick steps, the models, the entire model learns quickly and overfits to the training data. So to slow the pace of learning, we introduce this shrinkage parameter, lambda. So this is obviously less than 1. If it is 1, then it overfits, right? So this is obviously less than 1, typically 0.1 or 0.01 or 0.001 and so on. It's a hyperparameter. So by introducing this hyperparameter lambda, we generate more number of H's. That means the base learners. We'll slow the number of steps taken towards the target, and we introduce number of base learners. So we are increasing the number of base learners because of this lambda. So the maximum number of estimators is again a hyperparameter. B you can set to the value that you like. So the algorithm terminates when either B is reached or when it's a perfect fit before that, right? Suppose you give B equal to 1,000 and within 400 trees, or by the time you build 400 trees, the residual becomes 0. Then what is the point in building 401st tree, right? So you stop either when the residual is 0 or when the stopping criteria, the number of trees B is reached. So that's the idea of gradient boosting. So pictorially, so at each step you generate a decision stump or a short tree with bias. And then each of those trees will have a prediction. The H0 is basically the mean of the target variable. H1 is the prediction from the first base learner. It is slowed down by a shrinkage parameter lambda. The second one is also shrinkage by the same parameter lambda. The weight is the same. If you have seen, all the base learners have the same weight lambda. Excuse me. Excuse me. So you sum that all up, you get your final prediction, which is H of X, capital H of X. And the residuals are given by, are computed as follows. Each residual that you try to fit. I mean, how are you generating this model? These base learners, you're not generating based on the original target Y. Instead, you are generating from the residuals, and the residuals have to be computed as well using these formulas, right? So this is a very powerful algorithm, and it works for any differentiable loss function. You just replace the residual with the pseudo residual, which is the gradient, and it pretty much works like magic, right? So a few notes. Typically in boosting, the learners are homogeneous. They are homogeneous means they are all of the same type. So if you're using base learner as a decision tree, then other base learners are also decision trees. And to regularize further, we typically use decision stumps. Decision stumps are trees with depth 1, or we keep it short with typical depth 2, 3, 4, or 5. Certainly, we are not going to grow the entire tree. So that's an important point to note. And the second point to note is that the pseudo residual that we compute at each baby step kind of indicates how difficult it is to fit the item using the base learners, right? Don't you think so? If the prediction is far from the actual target value, that means it was difficult for that data item to be predicted correctly, right? So the gradient, in some sense, gradient is basically the pseudo residual, in some sense can be thought of as the relative weight of the data item, right? So this is a very important concept which we will use in the next topic, right? So the gradient essentially provides you with a weight for the data item. The more difficult the data item, the higher the gradient or the higher the residual, right? I mean, same thing in the class also, right? I will give a very crude example. In the class, some students who are the target is to get an A plus, right? Some students have a huge residual. They are probably C minus or something like that. So these students are the targets. I mean, they kind of the professor needs to, the instructor needs to focus more on these students, right, who are far away from the goal of A plus. So that's the reason why I have this slogan in my class: not to leave any student behind, right? We don't want to leave any student behind. The idea is to focus on the students who are having difficult time by giving greater weightage to them. For instance, I asked my TAs to talk to these students who are having a bit of difficulty, to bring them up to speed, to help them, right? So we give more weightage to the students who are having difficulty. The same thing is done in boosting as well. So there's a nice playground for gradient boosting, which I thought I will show you. So you can choose the depth. So if you choose the depth as 4, you get this complex decision boundary. The idea is to, I mean, this is a classification problem, though we discussed the boosting in terms of regression. Here, this example is for classification. So we want to classify the blue points from the orange points. So basically, because these are all decision trees, the decision boundary is rectangles, 2-dimensional rectangles, right? If it is n dimensions, it will be hypercube, but in 2 dimensions, it's rectangles or squares, right? So you can see this is a complex decision boundary, right? It's a circle basically, but of course, because of the decision trees, you see squares or rectangles. So it is pretty good accuracy. The tree depth is 4. The learning rate, which is lambda, is 0.1. Of course, we are not rotating the data set. The number of trees is 50. These are all hyperparameters that you can configure. So if you increase, so there is some misclassification, if you have seen, or rather some points have been left out. Like these blue points are left out. These white regions are not classified still. So if you probably increase the number of trees, yeah, those points also get classified. So 50 was too less a number to cover all the data items. Each point is a data item. Each point is a row, right, in the data set. So, and what happens if you increase the depth of the tree? If you increase the depth of the tree, 100 trees are also not sufficient, looks like. Some regions are left out, right? And probably some misclassifications because of overfitting. No, not yet. Maybe this is not a good example for overfitting. But this is a very good visual example of how this boosting works, gradient boosting works. So if you want to look at the decision boundary for 1, 2, 3, 4 trees, this is the decision boundary for the first 4 trees. As you can see, a lot of data points are not even classified yet, but most of the data points classified so far are a good fit. It's doing pretty good. 5 trees, 6 trees, 7 trees. You can see, you can visualize all this stuff. So it's that's how gradient boosting works. Okay, to summarize in a flow chart, so we are given a training set, and we choose hyperparameters. L is the loss function. We want we want our algorithm to apply to any loss function, not just the squared error. Lambda is the learning rate or the shrinkage parameter, regularization parameter. H is the hypothesis space. Capital H is hypothesis space. That means we don't want to restrict ourselves to just decision trees. We want to be free to choose any learner, base learner, which belongs to the hypothesis space, right? And H is the base learner in this hypothesis space. A is a function to find the base learner. So the algorithm to generate the trees, for instance, is your A. And B is the number of base learners. and we start by setting small b is equal to 1. This is the loop variable. B is the loop variable. So we iterate for b number of times. So this is what the decision point is doing. So essentially we are iterating for b number of times, and at the end we are going to return the final sum of the generated predictions, H, capital H, like we saw in the previous one of the previous slides. But what are we going to do at each iteration? First is we are going to compute the gradient with respect to the predicted value, right? And if the loss is squared error, it is the residual. So the gradient essentially tells us how well the base learner fits the specific data item. Or to think of it the other way, how difficult it was for the data item to be classified. It kind of indicates the weight that we give for the data item. And then the algorithm for generating the decision tree or decision stump itself is mathematically represented like this. But because we don't want to restrict ourselves to decision trees or decision stumps, we talk generally in terms of a function A, which minimizes the loss. In this case, it's a residual squared error loss, which minimizes the sum of the squared errors for an argument H. So each iteration, we are going to find an argument H, which is the base learner, which minimizes the sum of the squared errors, or any loss function for that matter. But in this case, we just chose the squared error, right? So that's the idea behind. So this box essentially for our decision trees, you can think of this box as generating the decision stump. So the split value, you know how to generate the decision stumps, right? Gini index or entropy. So we are going to use those kind of things to minimize the loss. And then we boost our prediction, this final value, each step by adding the regularized prediction from the base learner. So HB of X is the prediction from the base learner. We shrink it by a factor of lambda, which is the learning rate, which can be thought of as the learning rate. And we sum it up to the previous value. So that's what is done. So this is essentially the idea behind gradient boosting, right? Everyone with me so far? So if you have noticed, boosting is yet another gradient descent. So there's a paper by these authors which gives the mathematical detail for this conclusion. But intuitively also, right, by now you would have realized that these baby steps and gradient, computing the gradients, all these would have already reminded you of gradient descent way of minimizing the loss, right? So this is basically gradient descent. So just to remind you or refresh your memory, so we have this loss function, which is like this huge mountain with valleys and all that stuff. We want to reach the bottom of the valley, right? So this is the hiker who's trying to reach the bottom of the valley. Right now he's at point W, which is the weight vector. So the hiker in this case must go left on the horizontal axis, right? He must go like this to minimize the loss. So that means W must be less, right? So we need to decrease W in this position. So if the position is here, the slope is negative, and the hiker must go to the right. That means increase the value of W. So in the previous case, the slope is positive, and W must decrease so that the hiker goes left. In this case, the hiker goes right and the slope is negative, and we need to increase W. So how can we express the last two slides in one line in math? By using this equation, right? This is basically the direction of the slope, or this is the slope. This is the stride towards in that direction. And then the previous value of where the hiker was standing, the new value, right? So the derivative is the slope of the loss function. Lambda, it should have been lambda. Lambda is the length of the stride in the direction of the slope. If slope is positive, weights decrease and vice versa. And if you extend, I mean, there's just one dimension, right? But if you extend it to multi-dimensions, instead of the derivative, we are going to use gradient, right? So that's why it's called gradient descent. And this should remind you of our gradient boosting. So this is basically the gradient, and residual is basically the negative gradient. So this is essentially a different way of putting the gradient boosting, right? So gradient boosting and gradient descent are not too different from each other. Okay, now let's talk about Adaboost. This is obviously a boosting technique as well, a pretty popular one. And in fact, Adaboost was invented before gradient boosting. So what are some of the, how do you compare Adaboost with gradient boosting that we talked so far? So both take baby steps. So baby steps are base learners, and these base learners are typically decision stumps in both cases. And in Adaboost particularly, these are decision stumps, right? So instead of shrinking the trees using a constant value in gradient boosting, it was a constant value lambda, right? For all the stumps, or for all the base learners, the shrinkage parameter lambda was constant. But in Adaboost, we are going to use a weight, relative importance, alpha, that is proportional to how well the base learner performs. So how do you know how well the base learner performed? How did we know how well the base learner performed on a particular data item? In gradient boosting. So the residual, or the gradient, right? The gradient of the residual tells you how well the base learner performed. It tells you how far from the target value the prediction is. So in a sense, it is telling how difficult the data item is, or how difficult it was for the base learner to work with the data item. So gradient, basically. So we'll involve gradient in some way in that respect. So alpha is going to involve some component of gradient. So we are obviously, like in gradient boosting, we are going to combine the base learners using a weightage parameter alpha b, which differs for each tree. So here there's a subscript b. For lambda there is no subscript, but for alpha there's a subscript because it differs from base learner to base learner. Let me quickly check if there are any questions on the YouTube. This is not loading for some reason. Let me check. No subscript, but for alpha there's a subscript because, okay. There are no questions, I think. It's not loading, but I don't think there are questions. Okay, fine. Or at least I'm not able to see any. The chat window is not loading. Okay. So just like in gradient boosting, we are going to combine the base learners with a weightage parameter, in this case, a different one for each base learner, alpha b, and we are going to sum up. And typically Adaboost is used for classification. So we are going to use the sign function to determine the class of the final prediction. So if majority, if this sums up to a minus value, then the prediction will be a -1. If this sums up to a plus value, the prediction will be a +1 class, right? So there's no big surprise here, right? There's nothing new here. We all know this. So the gradient, which indicated the relative importance of a data item, is now used to perturb X row-wise instead of Y. That is a big difference in Adaboost. So in gradient boosting, we use the gradient to perturb Y, the target variable, right? Instead of the original Y values, we use the residuals. But in this case, we perturb X. How do we do that? Any guesses? Actually, I gave the answer beginning itself. We are going to use the gradient to weigh the rows, right? We are going to somehow incorporate the gradient into the weights of each row. So that's how we are going to perturb X. So let us first talk about weighing the base models. That means computing the alphas, right? Alpha is the weight for the base model. So how are you going to compute the alpha? So let us start with a very basic probability question. What is the odds ratio of a model classifying correctly with probability P? So what is the odds ratio? Does anyone remember? So there is a question, there's a request on the chat window to start, to give a recap of what we did so far. I can quickly go over that if that is the case. So the summaries of gradient boosting is given in this slide. So we iterate across multiple base learners, and each base learner is a decision stump, right? Or a short tree, but certainly not a fully grown tree. So we start with high bias, right? And we repeatedly compute the gradient for each base learner. We generate the tree here, and then we boost our prediction each time by a shrinkage parameter lambda combined with the prediction of the base learner. So that is essentially what we are doing. So if there are any specific questions, and I can answer, but otherwise, let us continue. And if there is time, I will come back and give a overall recap of the whole thing again. So what is the odds ratio for a model classifying correctly with probability P? Yeah, P by 1 minus P, exactly. Thank you. So P minus 1 by P. It can also be written as 1 minus epsilon by epsilon. Why? Epsilon is the error, right? If epsilon is the error, the probability is basically 1 minus the epsilon. Probability of predicting correctly is 1 minus the error rate, right? So 1 minus E by E, or 1 minus epsilon by epsilon tells you the odds ratio. So the better the model, the higher the odds ratio, right? So if the model is better, the odds ratio will be higher as well. Now, because there is division and all that, we prefer to take division is one thing, and the other thing is with probabilities, logarithms works better. You all know that, right? The probabilities are values less than 1. So we take logarithm of the ratios to simplify operations. So multiplications convert to additions, and I think I missed a word there. Divisions convert to subtraction. Sorry, I need to rephrase this. So multiplications, you know that logarithm converts multiplications to additions, right? And divisions to subtraction. So that's what happens here. So that is the reason why we take logarithms. So when you take the logarithm of the odds ratio, it is called as a logit function. By now you would have recognized this as from where logistic regression gets its name, right? So logistic function is a reverse of logit function. And logit function is a logarithm of the odds ratio. So it converts a probability P, which is between 0 to 1, to a number R between minus infinity to plus infinity. Logistic function does exactly the reverse. It takes a value, a real numbered value between minus infinity and plus infinity, and converts it into a probability 0 to 1. And now this can be written as 2 times tan H inverse, hyperbolic tan inverse of 1 minus 2 epsilon. I mean, I don't want to go into the derivation, but you can check. I think if you look at the Wikipedia for logit function, I think this is where I saw. Yeah, you can see here. This logit function is basically is equal to 2 times tan inverse of this thing, hyperbolic tan inverse of that quantity, right? So there's a 2 here. So to get rid of 2, we don't want to deal with this unnecessary constant, right? Because the constants don't make a whole lot of difference. So we'll get rid of 2. But before that, the logarithm of the odds ratio is an indication of how well the base learner can classify, right? Just like the odds ratio, the better the model, the higher the odds ratio. So the higher, or the logit function kind of indicates how well the base learner is able to classify. So we can use it as a weight. In this case, alpha b for the base learner. So we are going to compute alpha b as half times the logit function. The half is coming because we don't want to deal with 2's and all that stuff, because we are going to get 2's in other places also. To avoid all that confusion, we are going to multiply it with half. So the weight of each base learner is given by this formula. The error from the base learner, 1 minus the error from the base learner divided by the error from the base learner, take a logarithm and multiply it by half. That is the relative weight for the base learner. So now next is to weigh the data items. Remember, we have to perturb the data items, X's, the rows in the training data set. And the way we are going to do it is by introducing a weight to each of the rows. Remember, we talked of this example of a student who is having difficulty. We give greater weight to that student. That's what we are going to do here. So initially, all the samples are the same way. When the class starts, the instructor is uniform across the students. Every student is equal. But after the first quiz, we know which student we have to focus more on, right? So we factor in alpha b into the subsequent weight updates. So alpha b is a logarithm. So we use exponentiation for the weights of the data items. So this wi indicates the weight for each data item. And in every iteration, we update the weight by this quantity. So for classification, what happens? For what do you conclude for classification? What will be the value of the weight update? In classification, if it classifies correctly, yi is equal to hxi, right? That means it predicted correctly. If it is +1, if yi is +1, hxi also is +1, correct classification. So that means the weighting factor is e power minus alpha beta, right? So that means we exponentially lower the weight for correctly classified data item. So if a student gets 10 upon 10 in the first quiz, we pay less attention, right? Something like that. Or in case of communism and socialistic ideals, if a capitalist is earning billions, then he is given a very low weightage compared to somebody who's struggling to make his ends meet, right? So that is a analogy here. So we exponentially lower the weight for correctly classified data items. And for difficult ones, we make the weightage exponentially high. If there's a misclassification, the prediction h of xi is not equal to yi. That means this is going to be -1. If this is +1, this will be -1 and vice versa, right? So the product will be a -1. So that means e power alpha. So we are going to make it exponentially high for misclassifications. So that's how we change the focus for the data items. So of course, we want the weights to be a distribution, right? You know the meaning of a distribution. The weights should sum up to 1. So we need to normalize. So we do a normalization. So the error is also normalized weights computed by using normalized weights. So what is the error of a model? This is the indicator function. Count the number of misclassification, multiply it with the weighted, with the normalized weight, right? That's what we are doing here. So compute the number of misclassification. That's what the I function does, indicator function. It counts the number of times yi is not equal to h of xi. It counts all those misclassifications and computes the weighted number of misclassifications. And the weights are normalized. So that is the error value. So this is the error update. This is the weight update. And in the previous slide, we saw the weight update for the base learner. So 3 updates. Now a question for you. How do the weights for the data items change with the progression of time? Can somebody tell me? So as time progresses, so this is the real decision boundary. This is the true decision boundary. Or rather, this is the eventual decision boundary that the ensemble will compute. Assume, I mean, this is of course, it won't compute the straight line. It's not a linear model, right? It's going to be a complex boundary, but I'm just giving an example. So how do the weights for the data items change with the progression of time? So there's a comment on the chat window, the pseudo error changes, so the weight changes. Yeah, exactly. The pseudo error changes. For each base model, the pseudo error changes, the pseudo residual changes. So the weights will also change. So how do they change? So which are the difficult points here? So you are given all these points. Which are the difficult points? The difficult points are near the boundary, right? These are the points which are hard to classify. You have to keep moving the line this way, that way, this way, that way, until you reach the correct, you minimize the loss, right? So these are the difficult points. These are all the A+ students. These are all good ones. So the weights for these points tend to 0. The weights for these points and these points pretty quickly tend to 0 because they're easy points, easy to classify. So these are the points which will continue to have a higher weight. So weights in the shaded region tend to 0 with the progression of time. So these are the easy points. So the weights will keep getting lower and lower. And these are the difficult points. The weights get, so you'll be focusing, the algorithm focuses more and more on these points. So in the context of active learning, this region is called as region of disagreement, right? So there's I don't know how many of you know active learning, but in active learning, there is a region of disagreement. So this is the region of disagreement which has all the difficult points. So now let us talk about the loss function. So the loss function we are minimizing corresponding to all these logarithms and exponentials is basically exponential, right? It's obvious. We are trying to minimize an exponential loss function, and the exponential loss function is essentially the exponent of yi times h of xi, right? So this indicates the number of misclassification. Yi times h of xi is basically a misclassification. Eventual h, you see the notation here. We are using capital H here and not small h. Why? Because it's not the base learning. This is the eventual. We are talking in terms of loss, not error. If it was error, this would have been small h. If it is loss, it is capital H, because this is a final classifier. So you count all the misclassifications, and to the power of e will give you the total loss. And the gradient you take is yi times e power yi, this stuff, right? Again, you apply chain rule. If you apply chain rule, this is what you get. So this time, we are still using the gradient, but to perturb x instead of y. And how are we perturbing x? By incorporating the gradient into the weight update of the data item. See the weight update of the gradient, the weight update of the data item, that is the row, has this gradient term, because yi is not there, but the component of that is there. So we are basically perturbing x by using this weight update for the data items. So essentially what we are going to do is we are given the training set xi, yi like before. We choose the hyperparameters. H is the hypothesis space. Small h is a base learner in the hypothesis space. A is a function like before to find the base learner. B is the number of base learners. So we first initialize the weights equal. That means 1 by n, because remember it needs to be a distribution, right? The weights vector is a distribution. So it has to sum up to 1. So 1 by n. And then we compute B number of trees, capital B number of trees, because we have to set B to 1. The small b should be 1 here. I missed that. So we adopt, we boost the trees adaptively. And the adaptation is basically accommodating the changes. See, the model has done something. Now, how do you adapt to that change? See, again, this crude example of a student not performing well. Now, you have determined that this student hasn't performed well. How are you going to adapt your teaching to better help that student? By increasing the weight, right? In the class, you focus more on that student. Or if the student is a bit reticent, maybe try to help him offline, right? Ask the TAs to talk to him. There are many methods. So we adapt our teaching, and we maybe will simplify our discussion. Maybe the math is too high to interpret. We'll try to simplify the math. But of course, if the student doesn't listen, that's a different matter. That is a real world problem, not with machine learning. Machine learning is much simpler. See, we started with saying that human beings are complex entities. You cannot simplify their behavior by using biases, right? So same thing here. Machine learning is a lot more simpler. Real world is a little difficult, but I'm just giving you this analogy to help you understand. So we adapt to the performance of the data item and the base learner by this weight. So this is the error update. We already saw what the error update is. So this, I should have removed this anyway. Sorry about this. This is irrelevant here. So then we compute the tree, the base learner, right? The same, minimizing the loss. The loss is basically, or in this case, sum of all the errors, right? So indicator function tells you how many misclassifications. We try to minimize the misclassifications. That is the function of A, which is essentially the algorithm of the decision tree, right? The entropy or the Gini index that you use to grow the decision tree is basically your A. And the idea of A is to compute the H, which is the argument in this loss function, which minimizes the loss. So that is the idea. And then we, like before, we boost our performance by combining the current prediction with the previous prediction, and we weight it with alpha. So that's the alpha update. Next is to update the alpha, right? We update the alpha using this formula. We update the weight also accordingly. So that's it. We do all these updates, and we boost our prediction in each round. And that's it. Eventually, you return the value of H. So there are many variants of boosting. Oh boy, there are a lot of slides. There are many variants of boosting. XGBoost, Light GBM, Cat Boost are the most popular ones. XGBoost came first, next Light GBM, and Cat Boost is the latest model. I think it came out in 2018, I believe. They use a lot of techniques, mainly for scaling to big data. So XGBoost uses some algorithms which are very effective with big data, large quantities of data, and faster processing, handling categorical variables. Like Cat Boost is very good at handling categorical variables. Missing values, and again, Cat Boost is very good at handling textual data also. Otherwise, you would have had to do all this TF, IDF, and all that. But Cat Boost does that all for you. They can handle textual data as well. Now, they differ in the way they generate the trees. The algorithm for generating the trees using Gini index and entropy, that is different. Then the types of trees that are grown is also different. Then the community support is also different. Why? Because XGBoost has been there for a long time. So there's a lot of community support for XGBoost. On Stack Overflow, you just post a question, you get back an answer pretty quickly. Not for the other tools, at least as of now. Things might change. And the hyperparameters provided by each of them is also different. And of course, the performance also is different. Cat Boost has shown some really solid results. So it is very good in Cat Boost as well. So the other approach is to start with the variance. So I know I'm taking going a little over the time, but feel free to stay if you like. I'll probably cover it briefly, not spend a whole lot of time. So we basically, bagging stands for bootstrap aggregation. As the name indicates, we perturb the value, the training data set by bootstrapping the x's, the rows of x, the features, right? The data items we bootstrap. So we start with high variance and reduce the model complexity. So we perturb X by bootstrap sampling. We use homogeneous base learners, typically decision trees. And these decision trees are fully grown, no pruning. That means high variance, overfitting. And the tree growth can be easily parallelized. We are not boosting in steps, right? These are not steps. We are growing the trees in parallel. We can grow them in parallel. So that's the power of these bagging algorithms. And the aggregation is by mean or mode. We already saw that. And bootstrap, this is a concept from bootstrap sampling, not specific to machine learning. Bootstrap samples generally leave out 1/e, which is roughly 1/3 of the population. So how do you get 1 by e? You take the limit of 1 minus 1 by n. What is 1 by n? The probability of each data item being picked up is 1 by n, equal probability, right? So 1 minus 1 by n is the probability of being left out. And as n tends to infinity, this kind of tells you the limit. The limit kind of tells you how many samples will be left out, and that is 1 by e. So 1/3 of the population is typically left out. So 1/3 of the population in the Bootstrap sample are repeats. That's what it means, right? So what does it tell you? Such samples are considered out of bag, right? They are not used for training that model. They're out of bag. So out of bag samples automatically provide the validation data set. No need for doing the train, test, split, and all that. So that is a small aside. It's not important. And we already talked what bootstrap sampling is. I don't want to repeat that. So the idea is you generate all these bootstrap samples. As you can see, the first bootstrap sample has some dots, colors repeated. Second bootstrap samples has some other dots, colors repeated, so on and so forth. So use each of these bootstrap samples to generate trees, fully grown trees, right? You grow a committee of fully grown trees. Why do you call them committee? Because they are going to vote, right? They are going to take a majority vote. So we take a bootstrap sample, we generate these trees from bootstrap samples, and we aggregate using mean or mode. For classification, we use mode. For regression, we use mean. That's it. That's the simple idea behind bagging. The key idea is perturbing the rows by using bootstrap samples. So instead of choosing the same data items each time, you choose 2/3 of the items. I mean, roughly, right? Because 1/3 is left out of bag samples. 2/3 are chosen because of bootstrapping technique. And then generate the trees. All these trees look different. Actually, they should look different. In this slide, they're looking similar, but they should look different if you have done it correctly. But there's a big problem. What is the problem? So bootstrap sampling implies the trees are identically distributed. Why? Because bootstrap samples are picked up from the same distribution of data. So the distribution of the trees is identically distributed, but they are not independent of each other. Why? Because you take the example of a predictor or a feature which is really very strong. So this feature is going to be on the top for all the trees, right? So the relative importance of the features are more or less preserved across the trees. That means the trees are correlated. So the trees are identically distributed, but not independent and identically distributed. That is a problem. How do you decorrelate trees and produce independent trees is the question. Next question. And the answer is random forests. We introduce another level of randomization, another perturbation, random subspacing. So instead of working with all the columns, we work with only a few columns randomly chosen for each node. I mean, it could be each node. Some papers talk about each node, and some papers, the original paper was for the tree, I believe, for the entire tree, but the improvement they made was for doing this for each node. So you choose these black shaded rows in each, for each node, right, randomly, and then generate the trees. So the rest of the stuff remains the same. So we perturb the columns by random subspacing, and we perturb the rows by bootstrapping, and we generate the trees. And then, like before, we aggregate response, mean or mode, to compute the final classification or the regression value prediction. So that's bagging. Now let's move to more interesting topic, which is stacking. We are getting closer to the most interesting stuff. And the cutting edge research going on. So stacking originally there are no perturbations at all in the data set. So what does that imply to you? If there are no perturbations, if you use the same model like decision trees, you're going to end up with the same decision tree again and again, which will not diversify, right? So that is the reason why stacking takes a different approach compared to bagging or boosting. Stacking uses heterogeneous weak learners, or they need not be weak learners. It uses heterogeneous learners as base learners, right? So the first model could be a decision tree. Okay, let us look at the slide. So we are going to use heterogeneous learners. So the base models could be a decision tree like before. It could be a support vector machines, logistic regression, naive Bayes, and so on and so forth, right? And then we are going to stack. Why is it called stacking? Because we are adding another machine learning model here called the meta model. Typically, we use logistic regression as the meta model or the meta algorithm to combine the outputs from the base learners. So that is the idea behind stacking. So we learn using one model at a time, like we did for all the ML models. And we combine by using a machine learning algorithm instead of just mean or mode, right? So essentially we are, like in Adaboost and gradient boosting, each learner, or rather in Adaboost particularly, each base learner has a different weight, right? Relative importance of the base learners was different. And we used a different technique to compute the weights. The alphas were computed using exponential laws. But in this case, we are going to compute the weights by employing a machine learning algorithm itself. So what does that mean? That means that these YIs, which are generated from the base learners, will be used as features to this meta model. Isn't that interesting? The outputs, the predictions from the machine learning algorithms, the base learners, will be used as features for the meta model. So that is the key. Those are some of the key differences, right? So in a nutshell, so here the original data set XI, YI without any perturbation. This is the original stacking. This is how stacking was originally proposed in the research paper, right? So no perturbations. You use these rows in the data set to train the base learners, H1, H2, and so on till HB. We use a capital B number of base learners like before, but these base learners are heterogeneous. That means they're all different models. Then interesting thing is we are going to use the predictions from these base learners as the features in the training data set for the meta learner. Look at the training data set for the meta learner. The features are basically the predictions from the base learners, and the Y surprisingly doesn't change. The same Y here will be used here also. The features are different, but the Y is going to be the same. Isn't that interesting? Because our final prediction has to match Y, right? So Y is not going to be perturbed, right? We are not going to do anything with Y. Y is going to remain the same. But for the meta learner, the outputs from the base learners will become the features. So the final prediction is given by the meta learner. So to train the model, this is what is done, and to test the model also during the test time also the same thing happens. The data set, the test data set goes to the base learners. Then the predictions from the base learners are used as features. Then those features are used to generate the prediction from the meta learner. So that's the final prediction. But there's a problem. Okay. So we are using the same data set implies the base learners are heterogeneous, so that they do not all learn the same, right? I mean, we already talked about it. And there is no randomization of any sort in the data set. So the chances of overfitting are really very high. There is no randomization at all, right? So we are heavily depending on the base learners. So there's overfitting. Now the solution is to use different data sets for the base learners using k-fold sampling. Rather, it should not be cross-validation, it should be sampling. So we already know what k-fold sampling is, right? So this is an example of two-fold data set. So the first fold of the training data set is used to train the base learners. And that is the first step. You train the base learners using the first fold. You divide the data set into two folds. One is called the holdout data set, and the other is the other data set. So the other data set is used to train the base learners, and the holdout data set, which is the second fold, is used to train the meta learner, right? That is the second step. And just like before, the same steps, the outputs from the base learners will be the features for the meta learner. So initially the base learner is, the learners are trained using the first fold and the second fold. In the first fold, the meta learner does not even come into picture. In the first step, the meta learner does not even come into picture. Comes into picture only in the second fold, second step, right? The second step, we train the meta learner, and the remaining stuff remains the same. Now, an improvement is to use k folds of the data set. That means the rows are divided into k parts, divisions, and k minus folds are used for training the base learners, and the kth fold is used to train the meta learner. So this is a slight variation. But essentially, I mean, the idea is to not overfit, to reduce the overfitting as much as possible. That is the idea of this k folds. Okay, you can stack models in any number of layers. So this can be the base learner, this can be the second level of base learners, and then you use the final meta model to do the prediction. So that is called multi-level stacking. So does that remind you of anything? Does this remind you of anything? Multi-level stacking? How about this? Does this remind you of anything? Yes, artificial neural network. So an artificial neural network looks very similar, right? So multi-level stacking, that's what happens in artificial neural networks. So these inputs are all combined linearly, and you introduce a non-linear node in the middle, right? This could be a logistic function, or some kind of non-linearity is introduced. And then there's another layer of so there's a message on the chat window. Could you repeat step 1 link to step 2? So step 1. So in the step 1, you train the base learners, right? That is the only thing that is done. And how do you train the base learners? Use the first part of the training data set. So you divide the number of rows in the training data set into 2 parts. The first part will be used to train the base learners, right? In the second part, the base learners are already trained, right? Then in the second part, we only train the meta learner. And how do we train the meta learner? For the meta learner to be trained, you still need a data set. And that data set, where does that data set come from? From the base learners. The features are the outputs from the base learners, right? So the second part of the data set is passed to the base learners, like you pass the test data to machine learning models, right? That is exactly what you do. You compute the predictions, and for each row, there will be a corresponding row here, right? But instead of x1, x2, you will have the predictions made from the base learners, but the y value will be the same. And so the difference you should note is that the number of rows here is n, whereas the number of rows here is b, right? Why? Because there are only b number of base learners. So you use this training data set to train the meta learner, right? So you train the base learners first, use that model. That means you determine the weights of your support vector machine, all the parameters of the support vector machines, or the logistic regression, or whatever it is. You determine all those in the first step and use those in the second step to train the meta learner, right? So that is what happens. I hope that is clear now. So multi-level stacking is basically using multiple layers of models to generate the final model. So deep learning is essentially stacked learning, right? Ensemble, stacked ensemble. Deep learning is essentially stacked ensemble. So each of these will have an activation function, right? Typically a sigmoid function or a ReLU and all those functions, right? It's a non-linearity that you're introducing into pretty much linear combinations of the inputs, right? And the outputs from these are passed as inputs to the next layer. And the outputs from these are passed to the next layer. This is essentially what you're doing in stacking, right? Outputs from the first layer of models is passed to the second layer of models as inputs, as features, and so on and so forth. So your neural network or deep learning is essentially stacked learning. So that's a nice segue into using meta learning in the context of deep learning, because this is a big thing. It's a very hot research area. So I'll ask you a question, right? You have to tell me the language of the letter. You're given the language of this letter. This letter is A in Malayalam, an Indian language, South Indian language called Malayalam. This letter, I think it is A. That's how I remember. I'm a polyglot. I speak, read, and write multiple languages. So this is A, I think. Now, you're given this data. Now, can you tell me which language is this letter? Can somebody tell me which language is this letter on the right? Yeah, you're right. It's basically Malayalam, right? It's slight difference. There's a slight difference. It is Malayalam, right? So how were you able to tell this? I mean, human beings are able to tell this, but can machines do the same? So we know that this is Malayalam. Similarly, this letter is from Hebrew, and you're asked to tell this letter. So you're given a second letter, Hebrew. Then you're asked to predict this letter. Can somebody tell me the language of this letter? Is it Hebrew or Malayalam? It is obviously Malayalam, right? Because this looks quite different from Hebrew and much closer to Malayalam, right? All the curves and all that, they are closer to Malayalam, right? So this is Malayalam. Similarly, you are given a third language, and this is Gujarati, just one letter, right? So with one letter, we are being asked to predict the next letter. So which language is this letter? Can somebody tell me which language is this letter? Is it Gujarati, Hebrew, or Malayalam? So these are called ways. So right now we have 3 ways. We can go the Gujarati way, we can go the Hebrew way, we can go the Malayalam way. So this is a 3-way one-shot learning. You are given only one shot of each way, each class. Each class is a way. So, and you are able to predict, most of you will be able to predict that this is a letter from Hebrew, right? So how are you able to do this? So this is Hebrew. So can we make the machine learn in one shot like you did? Right? Just looking at one letter, you're able to tell the next letter that it is Malayalam or Hebrew and so on and so forth. Can the machines do the same? Can somebody tell me any ideas on how to do this? So what is a machine learning algorithm that comes closest to doing this? Anyone, any guesses? So a bigger example is, suppose you have this omniglot label data set. This is characters from many languages, but only 1 or 2 characters from each language, or maybe 3 or 4. So there's a few shot learning. So the number of samples provided to you are few. And for instance, this is, so this is I in some South Indian languages. This is ha in Kannada, I think, or ka, yeah, ha, I think, na, and all that stuff, right? So, so there you are given a few shots of data, and you have to predict. Now, suppose you are given this omniglot labeled data set. Each of these characters, each of these letters are labeled as Kannada or Hebrew or whatever, Greek and all that stuff. You're already given this labeled data set. Now, how do you produce an ML model to recognize a new letter not in the data set? This is what is called as one-shot learning. Can somebody, does anyone, so the one answer is neural networks, which is a good answer because neural networks is a universal function approximator. You can pretty much approximate any kind of function. So neural networks is a good answer, but you have to do a lot of work. Is there a simpler idea? Very simple idea. Any other guesses? Image processing, again, going back to neural networks. The answer posted on chat window is image processing, but again, you have to use, there's even simpler, right? Does this remind you of something? This is basically the k nearest neighbors classification. So the omniglot data set, the omniglot data set, these are all the points in the omniglot data set, green and all that, right? So if you are given a new data point, how are you going to determine its class? So you can use nearest neighbor algorithm, k nearest neighbors, and then all this stuff is there. But typically in k nearest neighbors, you use Euclidean distance, right? If you use Euclidean distance, you come up with this kind of decision boundaries, right? This is the decision boundary for 1NN. If it considers just one nearest neighbor, this is the decision boundary induced by a 1NN algorithm, right? It's called Voronoi diagram. Now, what is the problem with Euclidean distance? The problem is images. What is the problem with Euclidean distance or 1NN? The problem is distances become less meaningful in high dimensions. Remember, yeah, how does the machine find the distances from the letters? That's a very good question that needs to be answered. So Euclidean distance can be computed across images also, right? Pixel to pixel difference. You compute x1 minus x dash, x1 minus x dash 1 squared plus all that. If you do, you get the Euclidean distance, right? But that doesn't make much sense for pictures, right? For images, because it's pixel. and there's pixels are highly correlated. So Euclidean distance really does not add a whole lot of value, number one. And the other thing is distances become less meaningful in high dimensions. Like you see here, this is from a paper listed here. So the variance in the distribution tends to 0 when the number of samples, when the number of dimensions tends to infinity. As the number of dimensions increase, the relative distances become, or the difference in the distances become irrelevant. The variance, you can see the variance is decreasing as the number of dimensions is increasing. So this is a big problem. You cannot use Euclidean distances for pictures. So we need to compute, we need to come up with a different way. Like you said, we need to come up with a way to compute the distances. What if we compute the distances in the extracted feature space instead of in the original pixel space, or learn a metric space? So we are going to extract the features and we compute the features distances in the feature space, which are much more closer, right? Like in PCA, you extract features, right? In the principal component analysis, what you do is basically extracting the features, hidden features. So like that, if we can extract the features and then compute the distances between those principal features or principal components, those distances would be much more meaningful. So what does it tell you? It tells you that you need a layer of models to compute the features. You need to compute the feature space. Like in stacking, we computed the features for the next meta model, right? So we need to do something very similar. So can we build a neural network like was posted on the, somebody posted on the chat window? Can we build a neural network to classify based on the distance in the feature space? Is a question where I will end because we are really running out of time. And thank you for your patience. I'll still cover the rest of the slides, probably in my next talk, whenever a slot becomes available. But if you have any questions, these are my details. I have a web page and I'm available on Twitter and I'm generally searchable on the internet. You can always reach out to me. And if you have any specific 1 or 2 questions, I can take them now. Okay, thank you, sir, for such an insightful lecture. Thank you. It was really nice presenting this because I love this topic. Any other questions? Any questions? Okay, let me check the YouTube. Unfortunately, the YouTube chat panel is not loading for me. Yeah, the chat panel is not loading for me. If anyone has access to the, oh, you may not be. Okay, that's fine. Okay, there's another message. Thanks a lot, Professor, and let us know next session of the topic. Sure, I will post it. Oh, by the way, that reminds me. I usually end with my pitch on the chapter activities. So today's event was this meta algorithms in machine learning. And the next event is also a talk by me. It's a general introduction. This is an open house. So that means we are expecting general pool of audience as well from public, mostly to attract members for IEEE. So this is a more general talk on machine learning, an introduction, or for those who already have some background, it will be a refresher of machine learning through analogies, applications, and examples. It's an in-person event. If there's enough audience, we will have food catered. It's on the 14th of June in Semi in Milpitas. It'll also be broadcast virtually. So if you're interested, please do sign up. on Eventbrite. The link takes you, our website takes you to the Eventbrite link, and you can sign up there for this and future activities. So the activity for July is the conference. I don't have a slide prepared for it yet, but it's going to be a conference on applied data science. So please check out our website, and there is still time to submit papers if you're interested. Probably 1 or 2 more weeks is fine. 1 week is ideal, but we'll see. Depending on the number of papers you see, we might extend it by a week also. So that is the July activity. And August, we are going to have another conference. It's an annual conference of the chapter, New Frontiers in Computing. Typically previously was hosted in Stanford, but because of the COVID, the pandemic, we are going to host it virtually this year. The July event also will be virtual. And September will be in person. We'll have 2 great talks in Santa Clara University. We have reserved a conference room in Santa Clara University, and we'll have 2 talks which are co-located with a great conference as well that we are sponsoring. This conference is called Global Humanitarian Technology Conference, GHTC, IEEE GHTC. It's a signature conference. Please check it out and try to submit papers to that. And then we are always looking for volunteers for various things: editorial support, social media, publicity, if you're interested in any of these. And we have awards for volunteers and rising stars in the industry and all that stuff. So you can be part of all that. So with that, I thank you all for your patience, and it was nice talking to you all. Thank you, and see you in the future events.